A limiting distribution describes what happens to the n-step transition probabilities as n goes to infinity. We say that the chain has a limiting distribution pi if the limit of pij superscript n equals pi j for all starting states I. For a finite, irreducible, and a periodic Markov chain, the chain converges to a unique stationary distribution. This means that the long-run probability of being in state J does not depend on the starting state I. The chain forgets where it started. It is important to distinguish stationary distribution from limiting distribution. A stationary distribution satisfies pi equals pi p. A limiting distribution describes the limit as n goes to infinity. In many common finite irreducible aperiodic chains, they are the same, but not always. The periodic two-state example shows the difference. The transition matrix is row 1, 0, 1 and row 2, 1, 0. The stationary distribution is 0.5 and 0.5, but the chain starts in state 1. The distribution alternates between 1, 0 and 0, 1. It does not converge. So convergence requires more than stationary. A periodicity is needed to prevent oscillation. In this slide we are going to talk about absorbing Markov chains. An absorbing Markov chain is a chain with at least one absorbing state, and from every state it is possible to reach an absorbing state. These chains are useful when a process eventually ends in one of several final outcomes. Examples include a game that ends in win or loss, a machine that eventually fails, a customer who eventually leaves a system, or a project that eventually completes. For absorbing chains, we often reorder the states so that transient states come first and absorbing states come last. After this reordering, the transition matrix has a block form. It is P equals QR0I. Here Q describes transitions from transient states to transient states. R describes transitions from transient states to absorbing states. The zero block means absorbing states do not go back to transient states. The identity matrix I means absorbing states stay where they are. This block structure is very useful. It lets us compute two important quantities: the probability of absorption in each absorbing state and the expected time until absorption. The main questions are: where does the process end and how long does it take to get there? Let's talk about fundamental matrix. For an absorbing Markov chain, the fundamental matrix is defined as n equals I minus q inverse. It can also be written as I plus q squared plus q cubed, and so on. The matrix Q describes movement among transient states. Q squared describes two-step movement among transient states. Q cubed describes a three-step movement among transient states, and so on. When we add I plus q squared plus more terms, we count expected visits to transient states before absorption. The entry Nij has a clear meaning. It is the expected number of visits to transient state J starting from transient state I before the chain is absorbed. The interpretation is very helpful. The fundamental matrix summarizes the total expected transient behavior of the chain. It tells us how much time the process spends in different transient states before it reaches an absorbing state. The inverse formula n equals I minus q inverse is usually um, the practical way to compute it. The infinite series formula explains why it has this meaning. Okay, now let's talk about absorption probabilities and time. Uh, Once we have the fundamental matrix n, we can compute absorption probabilities and expected absorption times. The absorption probability matrix is B equals NR. The entry Bij is the probability that the chain is eventually absorbed in absorbing state J starting from transient state I. The expected time to absorption is T equals N times 1, where 1 is a column vector of 1s. The entry Ti um, is the expected number of steps until absorption when starting from transient state I. The slide gives a simple two-state example. The transient matrix is row 1, 0 0.7 and 0 0.3, and row 2, 0 and 1. State 2 is absorbing. Um, the transient block Q is just 0 0.7 and R is 0 0.3. Then N equals 1 over 1 minus 0 0.7, which is 3.333. The absorption probability is B equals NR, which equals 3.333 times 0.3, so B equals 1 here. This makes sense because state 2 is the only absorbing state, and eventually the chain is absorbed there with probability 1. The expected absorption time is T equals 3.333 steps. Um, Intuitively, at each step, absorption occurs with probability 0 0.3, so the expected waiting time is 1 over 0 0.3. Okay, in this slide, we want to talk about uh, birth-death chains. A birth-death chain is a Markov chain where transitions are only allowed between neighboring states. From state I, the chain can move to I plus 1, move to I minus 1, or stay at I. I plus 1, I minus 1, or stay at state I. We write P of I to I plus 1 equals Pi. This is often called a birth probability. We write P of I to I minus 1 um, equals Qi. And this is often called a death probability. We write P of I to I equals Ri, the probability of staying in the same state. These probabilities must satisfy a Pi plus Qi plus Ri equals 1. Birth-death chains are useful in many applications. In queuing theory, state I may represent a number of customers in a system. A birth is an arrival and a death is a departure. In population models, state I may represent the population size. A birth increases the population by 1 and a death decreases it by 1. In reliability models, state I may represent the number of working components. Uh, Um, okay, the advantage of birth-death chains is that transitions are local. The chain can only move to neighboring states. This makes the model interruptible um, in some times, but it also makes the model easier to analyze and also more explainable. So far, most of our discussion has been about discrete time Markov chains where transitions happen at times 0, 1, 2, and so on. In continuous time Markov chains, transitions may occur at any real time. We write the process as x of t for t greater than or equal to 0. The Markov property is similar given the present state at time s. The future after time s does not depend on the past before time s. A finite continuous time Markov chain is described by a generator matrix, usually written Q. For I not equal to j, Qij is the instant. Okay, for continuous time Markov chains, transition probabilities satisfy differential equations. These are called the Kolmogorov forward and backward equations. The forward equation is p prime of t equals p of t times q with initial condition p of 0 equals I. The backward equation is p prime of t equals q times p of t, again with p of 0 equals I. The forward equation can be interpreted as um, updating probabilities by looking at rates out of current intermediate states. The backward equation can be interpreted as updating probabilities by looking at rates out of the sorting state. For finite homogeneous continuous time Markov chains with constant generator Q, both equations have the same solution, P of t equals e to the qt. This is the matrix exponential solution. The analogy with discrete time is useful. In discrete time, n-step transitions are computed using p to the power n. In continuous time, transition probabilities after time t are computed using e to the qt. This topic is more advanced, but the key message is simple. Continuous time Markov chains replace transition probabilities per step with transition rates per unit time. Okay, now let us connect Markov chains to estimation. Suppose we observe one or more sample path of a Markov chain and we want to estimate the transition matrix P. Let Nij be the number of observed transitions from state I to state j. For example, if the chain is in state I 10 times and then moves to state j 3 of those times. Nij includes those 3 transitions. The maximum likelihood estimate of Pij is the number of transitions from I to j divided by the total number of transitions out of state I. So P hat ij equals Nij divided by the sum over k of Nik. This means each row of the transition matrix is estimated separately using relative frequencies. The row corresponds to the current state and the entries in that row describe the distribution of the next state. If some states or transitions are rare, the simple frequency estimate can be unstable. In such cases, smoothing or Bayesian priors can help. For example, we can add small pseudoconsts to avoid zero estimates. This slide also mentions hidden Markov models. In an HMM, the hidden states ZT evolve as a Markov chain, but we do not observe them directly. Instead, each hidden state generates an observation xt. Hidden Markov models are the topic of the um, next session. Okay, let us summarize the main points of the session. First, a Markov chain is a stochastic process where the future depends on the present state, not on the full past history. This is the Markov property. Second, the transition matrix P controls one-step movement. The entry Pij is the probability of moving from state I to state j in one step. Multi-step transitions are controlled by powers of P. In particular, P to the power n contains all n-step transition probabilities. Third, the Chapman-Kolmogorov equations explain how long transitions can be split into shorter transitions by summing over intermediate states. Fourth, the directed graph of a Markov chain helps us classify states. We studied accessibility, communication, communicating classes, closed classes, absorbing states, recurrence, transience, and periodicity. Fifth, stationary distributions solve pi equals solve pi equals pi p in many finite irreducible aperiodic chains. The distribution converges to the unique stationary distribution and the chain forgets its starting state. 6. Absorbing chains use the fundamental matrix n equals I minus q inverse. From n, we compute absorption probabilities b equals nr and expected absorption times t equals n times 1. Okay, for class discussion, try the exercises on the slide. These exercises, and you should send these exercises to my email by next week. Compute one-step and two-step predictions for a given 2x2 transition matrix. Use Chapman-Kolmogorov to derive a three-step transition probability. Find communicating classes in a three-state chain. Solve pi equals pi p for a two-state chain. Finally, for an absorbing chain, compute nb an expected absorbing time. Okay, for references, Ross Introduction to Probability Models and Ross Stochastic Processes are very useful. Norris Markov chains is also a strong reference for this topic. In the next session, we will study hidden Markov models and inference algorithms. I will wait for your questions. You can ask your questions in the group, and we can discuss about questions and exercises in an online meeting if you ask.